Yeah, and taking into account that this sequence is finite, not periodic. Then we calculated the extension where we assume that we repeat the same sequence multiple times, so it's periodic. We also calculated the correlation, autocorrelation for this case. And then we plot power spectral density for case with periodic signal. Another case, we start with autocorrelation function. And first task, we had to plot it. Then we had to evaluate what the possible values for second moment and first moment. And then we calculated power spectral density. And for the third task that we discussed, we were given this basis function, and then we had to calculate what's the amplitude of basis function so that it will be orthonormal, and then what's the autocorrelation function, and then what's the autocorrelation function of the signal, which comprises not only basis function but also sequence of random symbols. And in our case, it was a sequence of -1 and 1. So, and okay, and we also considered task number 4. I think it was short one. So we also had the discrete sequence of pulses. And then we had to evaluate first, second moments and power spectral density. And it was all for the last time. Today, we're going to start discrete modulation schemes. And if you have any questions, you are welcome to write in the chat, or you can open microphone. We still doing our seminars online. So let's see if situation changes. I will inform you if we go back to seminar room. So yeah, are there any questions? If not, then the corresponding set of tasks should be available on our Moodle web page. So please check it there. It is named as modulation task 6.1. So let's see. We have one task for the whole seminar. We have the following problem. We consider a two-dimensional PAM signal where PAM is the abbreviation of pulse amplitude modulation. PAM we can call as PAM. In this case, 2-bit sequence, Bn superscript 1 and Bn superscript 2 are transmitted in parallel by using orthogonal pulse shapes of phi1 and phi2. With T denoting the modulation interval, also called symbol interval, the transmitted signal is given by. And then we have expression for transmit signal. So we can write that our signal UTX of T equals, and then we have summation, infinite summation over different symbol intervals. And one symbol interval represented by two parts. The first part, we have 2Bn superscript 1 minus 1 in parentheses times phi1 T minus n capital T. You see that for each symbol interval, we have correspondingly shifted function or pulse shape function phi1 plus, and we should open bigger parentheses because it's still part of summation, plus 2b subscript n superscript 2 minus 1 times phi2 T minus n capital T. So it's written like this. And you see that we have two parts. We have first pulse shape function and corresponding multiplier, and we have second pulse shape function and corresponding to it multiplier. Also, immediately we can denote the quantity 2Bn superscript 1 minus 1 as Zn superscript 1, and also 2Bn superscript 2 minus 1 we know as Zn superscript 2. Just because later we will refer to this quantity and we will use it. Okay, and We also said that Bn1 and Bn2, they belong to alphabet from 0 to 1, 0 and 1. And Pal shape functions phi1 and phi2 also given. We can write them phi1 t equals to u0 times rectangular pulse t minus capital T over 4 divided by capital T over 2. First Pal shape function and second Pal shape function phi2 of t equals to u0 times rectangular shape function. Second rectangular shape function, but with different shift. T minus 3 capital T over 4 divided by capital T over 2. And that's all. U0 is voltage of our signal. So first part that we need to, and we have actually 10 questions. Okay, we start with the first one. We need to sketch the pulse shape phi1 and phi2. Okay, it's a simple task because we have just rectangular shape functions. So I specify symbol duration capital T, half of this interval T over 2. And we see that first basis function, no, sorry, it's not a basis function, it's pulse shape function. First pulse shape function shifted by T over 4. So it will be middle of rectangular pulse shape, pulse, and the width of the whole pulse will be T over 2. So it means that will be middle will be at T over 4, and duration will be T over 2. So we can place pulse. Maybe I make it a little bit smaller. Here is our pulse with amplitude U0, and it goes from 0 to capital T over 2. This is our first function, pulse shape function. And second pulse shape function, similar to it, but we have different shift for pulse itself. I also denote intervals from 0 to capital T, also denote T over 2. And we see that for second pulse, it will be centered at 3T over 4. So it's here, 3T over 4. And it also has width T over 2. So here's how it looks like. And it also has amplitude U0. This is our second pulse shape function. Pulse shape function. Okay, and now we can go to the next part. Now we need to show that phi1t and phi2t are orthogonal, but not orthonormal. So we can show this. I mean, in order to show that they're orthogonal, we simply need to calculate cross correlation between these two. Sorry, not cross correlation, but we need to calculate. Yes, it will be cross correlation for tau equals to 0, but we can also say that we need to calculate product or integral of product of these two signals. So we need to evaluate integral in general from minus infinity to infinity, but for this case from 0 to capital T between first pulse shape function and second pulse shape function over time. And of course, we see that if we look to these functions and we overlay them, I will copy, let's say, second basis function, and then I also copy first, so not basis function, but pulse shape function. It's important because it's the different quantities. I copy second part, and I also make it in different color. Actually, it's first part. 1 second. So I will make it red, and I will put above it of second pulse shape function. You see that they not overlap, that they occupy different time sub-intervals of our symbol interval. And as a result, we can, based on this, we can say that this integral of this product will be equal to 0. And it means, oops, maybe I put it here. It means that phi 1 of t and phi 2 of t are orthogonal. And what's the meaning of orthonormality? Why in which case we say that we have function basis orthonormal? It means that energy of each component equals to 1, or norm of each component in our basis equals to 1. And we know how to calculate energy. Yeah, we say that phi 1 equals to integral from 0 to capital T of phi 1 squared t dt. And if we calculate energy over symbol interval, what we get? We have amplitude u0, and it has duration from 0 to capital T over 2. Energy, as a result, will be u0 squared times t over 2. And we see that this quantity in general not equal to 1. No, it doesn't equal to 1. And as a result, we say that it's not orthonormal. Not orthonormal. Something similar we can do for the second pulse shape function, and we calculate energy. Will be u0 squared t over 2. And again, it doesn't equal to 1. And we also say that it's not orthonormal. Not orthonormal. And actually, if they are not orthonormal, but they orthogonal, we just need to normalize each pulse shape function in order to get the basis function. Yeah, and let's do it. Let's because we just need to do one more step. Yeah, you of course you remember from Gram-Schmidt orthogonalization procedure that if you have or not, but you can represent pulse shape function as energy of pulse shape function under square root times, let's say, first basis function. And also we can say that second pulse shape function can be written as energy. In general, it should be a cross correlation, but because pulse shape function is orthogonal, we can write it. It's energy times second basis function. So we can write it like this. And so we just need to divide by energy, square root of energy, in order to find first and second basis function. So we just need to take our pulse shape function and divide by square root of it, of its energy. And for second basis function, we also take its corresponding pulse shape function and divide by energy of this pulse shape function. So this is what we do. And yeah, we can just plot the resulting basis functions. Actually, nobody asked us about basis functions. but later on we will need them. So for this reason we calculate, or we try to find basis functions. So basis function, oops, it's wrong, it's completely wrong. It goes from 0 to capital T over 2. This is interval from 0 to capital T. Here we have capital T over 2. And amplitude, what will be the amplitude? I didn't write what's the square root of EO phi 1 and square root of energy for phi 2. So it will be U0 times T over 2 under square root for both cases. U0 times T over 2 under square root. And now we need to divide by this quantity amplitude of original pulse shape. And then we get something already familiar to us. We get that amplitude will be 2 over capital T for both basis functions. So now we have also information about how basis functions look like. And you see that they're orthogonal, of course. And actually, it's related to next question. Yeah, if you go to question D, we need to determine the relation between the modulation interval T and the bit interval TB. We can see interesting result or some feature of this modulation scheme, transmission scheme. That just to remind you, first part that contains first pulse shape function transmit first bit, and second part transmits second bit. So we have first pulse shape function for first bit, second pulse shape function for second bit. And now let's look to how they relate one to another. We see that actually they occupy different time ranges. We have interval from 0 to capital T over 2 for first bit. And we have interval from T over 2 to capital T for second bit. But we can see that actually these two intervals equal. The length of each interval is the same, and the length equal to capital T over 2. And during this interval, capital T over 2, we transmit only one bit. Yeah, and we can say during interval.
Sir, I want to ask one thing.
Yes, sure. Yes. What's the question?
Sir, in order to find basis functions of non-orthonormal pulse shape, we will be using same steps for finding these psi 1 and psi 2 always.
Psi 1 and psi 2. Do you mean if you have non-orthogonal pulse shapes?
Yes, these are non-orthonormal, as you have already proved earlier in B part.
Yes, they're orthogonal.
Yeah, they are orthogonal but not orthonormal. So yes, for finding basis function of such pulse shapes, we are going to use the same steps that you have shown here. Always.
Well, you always have a general procedure. You always have Gram-Schmidt orthogonalization procedure, and always in your mind, you always perform this procedure. But Of course, you don't need to show it explicitly, because when you do it, you can take some shortcuts, yeah? And for our Gram-Schmidt orthogonalization procedure, what we say? We say the following: take your first signal as your first basis function. Yeah, this is what we do. But then after you take it, you have to normalize it. You have to normalize by energy. And this is what we do here. We take our basis function. No, we take our pulse shape function. We normalize it by our energy, square root of energy, and we get first basis function. Okay, this is one-to-one first step from Gram-Schmidt procedure. Second step, we say that second signal is nothing else as sum of two basis functions, first and second basis function. But for this specific example, first basis function doesn't contribute in the second signal because they are orthogonal. As a result, immediately we can just exclude any influence of first basis function onto second signal. And as a result, we come to simplified version where we get that in order to find second basis function, we just need to, as for first step, just normalize the corresponding signal because they're orthogonal. And this is what we do. And then if you have third signals that are orthogonal to previous two, then you just continue, just normalize. But it could also happen that third signal won't be orthogonal to previous two signals. Then you have to perform a usual step for Gram-Schmidt orthogonalization. You have to calculate cross correlation and then subtract these parts that correlate with second and second basis functions from the third signal. But in general, if you have and many different signals and all of them mutually orthogonal, all pairs of the signals orthogonal, then in order to find basis, you just need to normalize each signal, and then you get basis for orthonormal basis for all these signals. So I hope I answered your question.
Yes, sir. It's clear.
Yeah.
Thank you.
Yeah. No problem. So let's go back. So we have during the interval t, we transmit 2 bits. And we see that for each, we see that each interval for both intervals for each bit, they're the same. And we can conclude that actually TB, time interval for 1 bit, is nothing else as simply capital T divided by 2. We just take the whole interval and divide it by number of bits that we can transmit during this interval. So, and yeah, this is the relation between TB and T. And of course, we can write it as T equals to 2 times TB. It also works. So, good. Then we go to part D. We need to determine the mean energy per bit, EB. E determines the mean energy per bit. It means the mean signal energy within a bit interval TB. Okay, now we need to find the mean energy. So, and yeah, we actually do very simple thing. We just first calculate what's the energy for first interval. Should be 1. And it will be equal to U0 squared times T over 2. Then we calculate energy for second interval, and it also equals to U0 squared times T over 2. From where we can conclude, actually, it's not necessary writing it this way, because previously we already said that the time interval for each bit is the same, bit interval is the same for both bits, and we can show that, or we can conclude that EPN superscript 1 equals to EP subscript n superscript 2, they equal, and it simply means that average energy per bit will be U0 squared times capital T over 2. Just based on this, that for both intervals you have the same amplitude, and that for both intervals they're the same. If it wouldn't be the case, then you can just calculate average between of this quantity. Then EB equals to summation over, let's say, I goes from 1 to do we denote? Okay, we don't have any notion for bit intervals, let's say capital I. Summation over EPN superscript I divided by number of possible bit intervals. Yeah, but then we can also, we just calculate sum of these two quantities, divide by 2, and we get this result. So this is our.
Professor?
Yes.
Please, I would like to know, does the value of Bn and B0 not affect the energy per bit? Say, let's assume if we had values of Bn and B0 which were different from 0 and 1, say 2 or -2, would it not affect the energy per bit?
Actually, yes, you are right. But let me, I think I skip it one step. Get in mind. Yes, actually, I skip it. It's a good point. Because yes, we transmit 0 and 1, but look at the original signal. Because here we modify actually, we can say that we transmit not Bn, original sequence of bits, but we transmit in the end sequence of this converted bits to Zn, yeah? And if we look to sequence Zn, maybe it actually makes sense to what is the value of Zn1. Zn1 was 2 times Bn1 minus 1. And Zn superscript 2 was 2 times En2 minus 1. Yes? And if original sequence was,
I think the value will be always 1 or -1.
Yes, exactly. This is what I tried to show. That we have Bn1, Bn2, and then we have, let's say, 0, 0, 1, 0, 1, 0, 0. And then I show how the corresponding sequence to Zn1 and Zn2 will look like. So if we have 0, we have 2 minus 1. No, 2 times 0 minus 1 will be minus 1. And for second, also minus 1. If we have 1, 0, we have 2 times 1 minus 1. It will be 1 and minus 1. And we can continue, we get minus 1, 1, 1, and 1. Simply speaking, this part where we multiply by 2 and subtract 1 from each bit converts our bit from 0 to 1 to the range from -1 to 1. And as a result, you see that actually each component contains the same, regardless what we transmit, 1 or -0 or 1, it will have the same energy. But if you wouldn't have such a block, which will convert from 0, which maps from 0, 1 to -1 and 1, then you just follow this expression that I have below. You calculate energy for each possible bit. And if you consider this case where we have bit n1 equals to, we say that n 1, B and 2 belongs to alphabet 0, 1. And just for a second, if we imagine that we would have transmission scheme where we have summation, and then we would just took Bn1 times pulse shape plus, of course, it should be also taken into account shift in time, but I just simplify this part. Yeah, for example, like this. Then during interval, when you transmit 0, you just transmit nothing. Your energy equals to 0. And during the interval, when you transmit 1, it will be U0 squared times T/2. Yeah, and then as a result, you see that the resulting energy will be resulting average energy will be even smaller. Now, this is a difference. But for this case, we have this mapping from 0, 1 interval to -1 and 1 interval. Did I understand right your question?
Yeah, yes, Professor. It's clear now.
Yeah. Yeah, this is the idea, but you can just yeah, this is what we have for this case, but in general, you just calculate energy over intervals, different energy for different bits, energy that you need to transmit for different bits, and then you just divide by number of how many bits in general you transmit during one single interval. Okay, and this is end of first part. Then we go to next part, to second part. In the following, we assume one short transmission. So we transmit only one symbol. We do not consider, it means that we do not consider and analyze transmission of the whole data sequence, but we instigate the signal only on the interval from 0 to capital T. So we have this range that we consider. So we only focus on the transmission of the 2 bits, P0 superscript 1 and P0 superscript 2. And there we have, now we come to discussion of signal space. So there are 4 possible constellations of the bits, B01, B02. Therefore, we can also distinguish 4 possibilities from S1T to S4T for transmit signal UTXT. And then we need to sketch the signal SIT for I goes from 1 to 4. Okay, yeah, I also made, sorry, I made, of course it should be 1, 1. It's type 1. It goes from 0, 0, and then it goes to 1, 1. Yeah. Thank you, Akash. Yeah, let's go back to our task. And actually, we need this table that I have shown here for this next part. So now we see how we map different bits to this intermediate quantity, Zn. And we can say how, I can also denote, maybe I will put this letter E nearby this table. And I will say that actually each pair of bits correspond to a specific signal. So as we said, but we transmit only 2 bits, B0 superscript 1 and B0 superscript 2. And we have, as you see, we have 4 possible combinations of 2 bits. And we denote first combination as S1 of T. Second combination, we denote S2 of T, and so on. So for each combination of bits, we say that it corresponds to specific signals that we transmit. And you see that what will be the intermediate quantities. And I can write how each signal, starting from S1 to S4, will look like in terms of pulse shape and then basis function. So I can write it as 1 of t is nothing else as -1 times phi1 of t plus -1 times phi2 of t. This is in terms of Pal shape functions, but I can also write it in terms of basis functions, and it will be -1 times what? Square root of e subscript f1 under the square root. It will be u0 times t over 2. u0 times t over 2. And you don't need to write all these details when you write answer during exam. I make all these steps just to make it clear and that you don't have any questions afterwards. So -1 times u0 t over 2 on the square root times the second basis function. Okay, so we can write something similar for second signal as of t equals to it will be 1 times first pulse shape plus -1 times second pulse shape function equals to 1 times e0 t over 2 on the square root by 1 t plus -1 times e0 t over 2 on the square root by 2t. Yeah, and then we just continue. I think actually I also do the following. I think I'm not only write it as sum. I need to squeeze this expression a little bit, and then I also write the result as inner product between two vectors. But then I need to have more vertical spacing. I need to increase it. So, and you see that maybe you should go back to first signal S1 that resulting sum. For the resulting sum, we can distinguish two parts. We can distinguish amplitude in front of each basis function, and then we can also distinguish basis function itself. Side one, side, and we can write this summation as inner product between two vectors. So we can say that we have. Now I need somehow. Place their inner product. Yeah, we can write it as we have. And also, let me simply, for simplicity, let me denote the quantity u0 t over 2 as EB under square root. And then we can write, we have first vector minus square root of EB. First element, second element minus square root of EB. First vector times I1, I2 of t for second vector, but I don't have place to write t. And for second signal, for S2, we can write something similar. We can write we have the first element of the first vector, square root of EB under square root, minus, and second element minus square root of EB under the square root, times by 1, by 2 of t. Like this. So we write it immediately in vector form. And we continue. Then I can write S3 of t. Then we can write for -1 first basis function, first pulse shape, plus 1 times second pulse shape function equals, and now write in terms of EB, it will be minus 1 square root of EB times first basic function plus 1 times E under square root second basic function, and we can write it as minus square root of EB square root of EB times 1 of t by 2 of t, like this. And the last part, the last signal as 4 of t, we have 1 pulse shaped by 1 of t plus 1 times pulse shaped by 2 of t. And we have first of EB times first basic function plus 1 times second basic function. And you see we have first of EB, first of EB, elements of first vector times 1 of t by 2 of t. So now we have everything ready for a signal space diagram. We just need to take scalars inside first vector and use them as coordinates of our points of signal space diagram. So, okay, we come back to this in a second, because actually in part E we had to sketch these signals. So, but anyway, we need all these writings just in a moment. But in order to sketch them, we can use this second step that we have here, that we just need to look. Actually, maybe for simplicity, we can even take first step. We just need to take scalar in front of each pulse shape and calculate sum of this resulting terms. And we can show that first signal as 1 of t and we have capital T over 2, 0. So we have minus phi1 of t, and originally phi1 was a positive pulse from 0 to capital T over 2 with amplitude u0. So we take negative pulse minus u0, and for second part we have minus phi2 of t, and also will be pulse also with negative amplitude u0 minus u0 t. And this is how resulting signal S1 of t will look like. S2 of t, we can just something similar. We take positive part, we have phi1 of t as it is, and then we take minus phi2 of t. We get this kind of signal. It goes from minus u0 to u0. The third signal. S3 of t. So we have minus phi1 of t plus phi2 of t. Minus phi1 of t plus phi2 of t. Like this. And also, here it goes from minus u0 0, and the last signal S4 of t we have phi1 of t plus phi2 of t plus phi1 of t plus phi2 and it has amplitude 0. This is our last S4 of t. Okay, so now we have all signals, and also we represented in the vector form the same signals. So what else? And now we go to part. So we need to sketch. I think we can go to part F. Based on the results from part B, determine signal space representation of the signals and draw the signal space diagram. So now we can use these quantities that we determined above in order to plot our signal space diagram for these signals. So along x-axis we say it will be our first basis function. Along y-axis we have second basis function. And let's take coordinates. So first coordinates will be minus square root of EB and minus square root of EB for second basis function. Let's denote that this quantity corresponds to square root of EB minus square root of EB along x-axis, that is. Let's take 6 cells. Minus square root. And also we can denote what is plus square root of EB and the square root. So first coordinate was minus square root of EB and minus square root of EB. So first point will be and show it as a vector that goes from origin to this point. And this corresponds to first signal, S1 of the vector S1. So then we go to second signal, S2 of t, and we have square root of EB minus square root of EB. So first component comes with positive, second comes with negative sign. S2, vector S2. Okay, then we go to third, minus square root of EB and plus square root of EB. This is S3, and the last signal S4, all components positive. And by the way, it's not unique. It depends on the way how you have chosen this sequence of bits, because you could choose different sequence of bits for S1 or S2 or S3 or S4. It's possible. But once you define it, what is S1, then you must be consistent. Then you must use this sequence of bits through all the same sequence through all your solution. Yeah. Again, this option is not unique. You could choose, for example, for S1 sequence as 1 and 1. It's possible, but once you have defined it, all your solution must be consistent with this option. Okay, this is our signal space diagram. Oh, and yeah, maybe we can also show what will be the detection regions. Yeah, because here it's easy because they will match axis. So along different axes we have different borders. And with these different colors, I show different detection regions. So we have 4 regions for detection. Okay, let's go further. Part determines the minimum Euclidean distance, the mean, between the signals as function of EB. Okay. Minimum distance, just based on its name, we just need to find what's the minimum distance between points. And of course, you see that if we just take points S3 and S4, S4 and then S5, S2, this distance will be a minimum possible. Because S1 and S4, distance between S1 and S4 will be larger than distance between S3 and S4. So minimum distance will be the following. This is the minimum distance. And we know that this projection of S4 onto x-axis is square root of EB. And knowing that this length is square root of EB, we need to find what's the length of this red interval. So first of all, actually we even don't need to do any additional transformations because we know that this one half of this interval corresponds to projection onto y-axis and corresponds to square root of EB. As a result, we can say, based on this is part G. T mean can be found as 2 times square root of EB. We just look to this signal space diagram and looking on it and knowing what's the projection on different axes, you just need to calculate, you need to find what's the minimum distance. And from here, we clearly see that minimum distance can be written as 2 times square root of EB. Okay, and that's all for second part of this task. And we go further. We come to the third part, and we have the following. Yeah, and if you have any questions, please let me know. But for now, I don't see any questions. So now we assume that the received signal y of t differs from the transmitted signal by additive by Gaussian noise n of t with the power spectrum density phi and n of f equals to n naught over 2. So it's constant. And we can say that our received signal can be written as mixture between transmit signal as I of t plus n of t. We have 2 components. Based on y of t, the task of the receiver is to decide which of the 4 signals as I of t has been sent most likely. A natural approach is to select the signal with the smallest distance to y of t. The minimum distance can be determined in a first approach by determining the energy of 4 possible different signals and choosing the signal which shows the minimum different energy J. Hence, the cost function is given by. So we have cost function which is given as integral from 0 to capital T. So we use correlator and we accumulate energy within a simple interval. And we calculate difference between our received signal. We don't know what the received signal is. We have just this some sampled or continuous voltage y t, and we subtract different candidates. We have 4 different candidates. We have S1, S2, S3, S4, and we have, in general, we should have 4 different branches, and for each branch we have its own candidate, and we subtract corresponding value Si of t. Then we calculate energy, we calculate square, and as I said before, we accumulate energy during simple interval. So this is what we do, and then we try to find the branch is the minimum possible output. Because if distance is smallest, then output will be also smallest possible. So, and actually it's already start of part H. That's the following. What's part 2? The question for part H is the following. Draw a block diagram of a detector which selects the most likely signal S hat of t, corresponding to following S hat of t equals to R. We need to find such argument that minimize our cost function. Or simply speaking, we need to find such S I of t that will minimize our cost. So, and in order to draw a block diagram, we need to modify slightly our cost function. We actually just open the parentheses and try to analyze what happens if we do this. So if we open parentheses, we can write result as 3 integrals. So we have integral from 0 to capital T by square of t dt minus, then we have cross product, and we have 2 times integral from 0 to capital T by t times Si of t plus, and third integral 0 to capital T Si squared t dt. So we get, instead of 1 integral, we get these 3 parts. And let's look to these parts. For all 4 branches, those components will be the same, because it's just energy of received signal, and it's independent on Si of t. And as far as it doesn't depend on Si of t, and as far as it's the same for all 4 branches, we can just ignore it, because it doesn't make any influence on the decision, because for all 4 branches we have just the same quantity, additional quantities, and all the same 4 branches. Then if we look to second term, this is actually, we calculate nothing else as correlation. Yeah, we already know how to calculate correlation, and it's exactly what we do here. We just take 2 signals and we calculate the integral of product. And this is what we do for correlation. And for this reason, the receiver called as correlator-based receiver. Yeah, it's based on bank of correlators. And inside each correlator, you calculate correlation. And let's look to the last part. Last part gives information about the energy of candidate, and it's constant. For our task, we consider it as a constant. Because for all candidates, we have the same energy. It has the same energy for all candidates. And we can ignore it, or we can say that for this task, it's independent. But if we just imagine that we would consider a case for unipolar signals, where we have for one signal we have 0, for another signal we have 1, then it would make sense. It would make sense to also take into account this part, the last part, because it would tell you where will be the threshold, when you make decision. And of course, when you make decision for unipolar signals, threshold will be somewhere in between 0 and 1. Point will be at 0.5, yeah? And this last term gives you information about threshold. But for this task, as far as all energy, the same for all signals, threshold will be at 0. And or simply speaking, we don't take into account this last term. So, and based on this, we see that actually second part, only second term, is important for us. And we can show how the resulting architecture will look like. So we have 4 branches. We have input signal Y. And then we divide the signal for multiple branches. So let's say we have we have 4 branches. And for each branch, we should do something. So what we do? First of all, we calculate product between input signal and so-called reference signal. And for each branch, we have different reference signal. So we have S1 of t for first branch. We have S2 of t for the second branch. We have S3 of t for the third branch, and for the last one, we have S4 of t. We have this bank of different multipliers. And then after we multiply our input signal with corresponding reference signal, we have to accumulate the energy of the result. And we do it by integrating over simple interval. We calculate integral from 0 to capital T, and then we integrate the result. In real life, you will use a low-pass filter for this purpose. On this purpose, so you remove all higher frequency components and you keep low frequency range. So for each branch, we have its own integrator. Okay, and afterwards, we have to find here we have interesting results. Originally, actually, we were searching for minimum of our cost function. We were searching for a minimum between minimum distance between y of t and si of t. But if we look to the inside after we open parentheses, we actually see that we can minimize the original cost function if we maximize output from correlator. So we want to minimize cost function j, but this minimum of cost function will correspond to maximum from correlator. So instead of minimizing the cost function itself, we try to find branch which contains maximum after correlator. And as a result, we can say that what we actually do, calculate or we try to find maximum branch, it contains maximum output. This is because we analyzed our structure and we, instead of finding minimum cost function, so that we can just quantity that actually corresponds to maximum. Okay, and the branch that contains maximum possible output will be our decision about what signal was transmitted. Okay, are there any questions about a correlator, about a receiver based on the bank of correlators? Okay, so let's go further. It was part H.
One question.
Okay, I think there is a question.
We are integrating and selecting only energy part. So, so will it be like negatives and positives?
Cross, yes, yeah, it's kind of energy. What's the question?
So we will be having negatives and positives. So that is the reason we can deduct which is being transmitted. Is it like that or?
No, we actually, I mean, I would say, even if original signal was negative, let's say it was like this. I think it was S1, minus, yeah, like this. But then after you calculate, and let's say we consider corresponding to this signal correlator, where you have also the same. Now this is corresponding correlator, which contains also two negative parts. After multiplying these two components, two signals, you will get this multiplication. You will get signal with two positive parts. And as a result, after integrating, you will have some big positive quantity. But if you get negative quantity, it means that actually your candidate is far away from, so it's unlikely that this candidate actually is what we transmit. This is the meaning if you get some negative value, taking into account that for all other branches, some of other branches, you have positive values. It simply means that it's unlikely that this is actually what we transmitted. Because even if original signal was negative, after calculating this correlation with correct correlator or with correct reference signal, you will get positive quantity. And yeah, it works fine. It works perfectly. Did I understand right your question?
Yeah, I was just thinking, so if we transmitted Y and we are making the calculations in between and like estimating what is being transmitted. So I thought if these S1, S2, S3, S4, some of them might be negative.
Could you please speak louder, because I barely hear you.
Yeah, can you hear me now, sir?
Yes, I think now it's better. It's much better.
Yeah, I was just saying if Y is transmitted and we are estimating is S hat at the end. So we are using this basis functions. I mean S1, S2, S3, S4, and
No,
I thought
basis functions. Sorry, they're not basis functions.
yeah, yeah.
They are signals that they are all possible range of signals that we have, but they are not basis functions. Scheme these basis functions will be in next subtasks. Just to clarify.
Okay, okay. Yeah, I think that is answering my question. I was just thinking only on the integral part. If we are having negatives, then how it can say even the example that you said, negative, negative, and finally we are getting a positive one. So are we estimating correctly which is being transmitted? So that was my question.
Your question is absolutely right if we consider basis functions. This is slightly different because here we are considering all range of possible signals. And actually this is very this implementation is very expensive because if you imagine that you use QIM 1024, where you have 1024 possible signals, then you have to have a correlator, bank of correlators that contains 1024 possible correlators. It's very expensive, but it works good. The performance is very, very good, but it's very expensive. And of course, I don't think that anyone doing it in typical applications. And instead, we actually, what we are doing, we just decompose for basis functions. Yeah, we decompose for typically 2 basis functions, and we just then look to output values instead of analyzing thousands of possible signals.
Okay. Yeah.
Yeah.
Understood.
This is the point. That each reference signal corresponds to specific signal in our signal space diagram, but not basis function. Yeah.
Okay.
Explain. Yeah. I hope I answered your question, Akash, but please let me know. Yeah. So there's also a question in the chat. Could you explain it once again about max block? Because even as argmin J, it is meaning why we take max. Yes, I mean it was minimum of cost function. So we try to minimize the distance. So we try to minimize this distance between the y of t and si of t. This is what we try, or okay, not minimize distance, but we try to find the candidate which has minimum possible distance. And what it means, so we still have this big expression below, and we try to find minimum of this expression. But if you have minimum of expression, let's say j, it corresponds to maximum of u, where we can write j equals to constant minus q. So the problem where you try to find minimum j, try to find such q that will be the largest possible, because if we have largest possible q, the difference will be, of course, it will be small. Yeah, the value that corresponds to minimum j corresponds to value where you have maximum q, because this is the difference. Larger q you have, smaller difference will be. And this is exactly what happened. We have term, first term is a constant, this integral of y t squared. This is constant, and then we subtract some quantity. And then larger than this quantity will be, larger second quantity will be, the smaller resulting value we get. And this is why we replace it minimum by maximum, because we replace the problem of finding minimum distance by finding maximum possible correlation. And this is what we did. We just replaced this original problem by finding maximum possible correlation. For this reason, we replaced minimum of cost function by maximum of correlator. Yeah, it was the idea. Okay, let's go further. We still have two subtasks. And for part I, counts as follows. In fact, however, the detector can be further simplified. Just 2 correlators are sufficient. These correlators produce the projections of y of t into our signal space. Thus, the detector first generates the 2 vector components. So instead of calculating correlation for all possible signals, we do the following. We calculate correlations only for 2 basis functions. We just calculate correlation between input signal and first basis function and we calculate correlation between our input signal and second basis function. So you see that instead of 4 correlators, now we need only 2 correlators. And then we try to solve simply a slightly different optimization problem. We try to find such argument that minimize difference between vector y minus si, absolute value, just absolute value, and try to find such candidate si from our set of possible signals that will minimize this result. And now we need to plot the corresponding diagram. And actually, it will be the answer to the question of Akash, yeah, because now we need to deal with this problem that even if the result is negative, but it's close to 0, then we should take it into account. And actually, instead of maximum as we did above, we have to still calculating minimum. So, how the resulting diagram will look like? Actually, I just need to repeat almost the same diagram as before. We have input signal y of t, and then we have 2 correlators. But for first correlator, we multiply input signal with the first basis function. And for second correlator, we multiply our input signal with the second basis function. Then we accumulate energy, so we calculate integral over symbol interval and we get 2 quantities. We get quantity y1 and we get quantity y2, and we combine these two numbers or we group them into a vector y. So we say that vector y, I can show it below, vector y equals group with y1, y2. And for simplicity, we actually just say that after we calculate the outputs, we just need to find such s that will have minimum possible value for difference y, this vector y that we have at the output after correlator, and candidate si. And si represented by 2 parts, 2 components. One part for first basis function, another part for second basis function. And the minimum value will correspond to our estimate. And how does it work? Now let's try to analyze how does it work based on a signal space diagram. Okay, we have this very nice picture, but actually what happens, it's not clear. So, and it should be easier if I plot signal space diagram and we try to analyze example. So, remember, we have 2 basis functions, psi1 of t, psi2 of t, and then we have 4 possible points. Okay, what was? Here we go, S1, S2, S3, and S4. 1, 2, 4, S3. Actually, I should change color because typically we say that we have this green points that correspond to correct positions, then we have the red point that correspond to noise. And I show the corresponding vectors. Actually, I should say that it's and all of these points given notation in vector form. It's underbar below. Okay, we have these 4 points. And then imagine that we received the sample. Let's say this is our sample that we receive. This is our y. Then this is what we have received after calculating correlations, our vector y, because y of t itself is continuous signal. But after we calculate correlation and we put these 2 components, y1 and y2, onto signal space, we get this point y given by this red point. Yeah, this is what we have. And then actually what we are doing next, we calculate difference. We calculate difference between this point that we have and all signals that we have in our constellation. Calculate difference. So it was y minus x1. Yeah, it will be vector pointing in this direction. Then it was y minus s3. It will be such vector. Then it was y minus s2 and y minus s4. So we calculate all these vectors. And actually, what is our goal? Our goal is to calculate the length of each vector. So we have to calculate absolute value squared because we calculate length. But we remember that actually length is proportional or has, yeah, how it says, I mean, all ratios for length. Yeah, we can call it as proportional. We can say that length will be kind of proportional to absolute value of difference between 2 vectors. And for this, but at the same time, calculating square value of something is computationally expensive. It's more expensive than calculating simply absolute value. And then we say that okay, we don't calculate length, but we just limit ourselves by calculating absolute value. But the result that we get will be exactly the same as we would get by calculating the length, because what's our goal? Our goal is to find minimum. Our goal is to find argument that corresponds to minimum. And if we have minimum quantity for length, the same minimum quantity will be for absolute value. And this is kind of approximation that we do here to simplify our computations. And then our original problem, as I said, was calculating length. And then we choose such candidate that correspond to minimum possible length. Then you see the actual length between vector y and s1 will be smallest. And as a result, we take candidate s1. For this case, we take S1 as our decision of what was transmitted, because it's closer to what we have received. And this closeness we evaluate by analyzing absolute value of difference. So there's question, we need to calculate Euclidean distance. Yes, right, this is exactly what we need to do. We need to calculate Euclidean distance. But we can simplify it. We can simplify this calculation of Euclidean distance by analyzing absolute value. This is the idea. And remember that for Euclidean distance, you get one number, but here for this task, you calculate absolute value, and you get the vector of absolute values. And it also gives you another advantage that you can parallelize. So you just analyze each number in your resulting vector separately, and you just choose. You just choose for each. Actually, in our vector, each number corresponds to a separate basis function, and that means that you just choose for each basis function closest possible candidate separate. I hope it's clear, but please let me know if it's not. Yeah, the main point is actually, yes, we need to calculate Euclidean distance, but we relax this problem. We simplify it, and instead of calculating Euclidean distance, we calculate absolute value of difference. And the result, surprisingly, we get the same result. Because for us, important not distance itself, but for us, it's important to find closest possible candidate. The y vector near to S1 is one instance. We can also take y vector anywhere in the space. Yeah, I mean, this red point shown here is just, yeah, you can place it at any point on this diagram, and it just represents a random sample of voltage that you received. You have some random signal, you don't know in advance what was transmitted, you place it, and we can just place another signal. This is, let's say, if let's denote it as y1, let's say first sample, but we consider all samples independent. Then we have this vector that corresponds to another sample. And then what you do again, you just calculate distances between this point and all points in our constellation. And you try to find the closest possible distance. And of course, in this case, you see it as 4. You have closest possible distance. And it means that it will be our decision for what was transmitted for second interval. And previously it was our decision for what was transmitted during the first interval. This is the idea. Okay, and yes, I hope it's clear. It's clear. And the last part that we have for this problem that we need to, okay, yeah, let's just answer this question. So last part is the received vector y can be decomposed into a signal component Si and a noise component N. It means that the projection of Nt into our signal space, it means that the projection of Nt into our signal space. And we need to determine expected value of product Nj times Nk. So let's try to analyze the last part in our question. So we have the following. So we have noise component. So we have what actually we know? We know from the beginning of the last part that we have power spectrum density of noise given by N0 over 2. What about the case when our signal is located in the middle between two S? Then you have to decide. Then you have to decide in your system what you do when you have voltage exactly between two quantities. Typically, you say that where was our? That let's say if we exactly on the threshold between S4 and S3, we make decision for S4. When we in between S3 and S1, we make decision for S3, and so on. You just need to specify by yourself, and then it's not a problem. But in reality, it never happens. Or small probability you get voltage exactly on threshold. Okay, and what do you know for the last part? That we know that pass packet density, and yeah, I mean, if you, I would say that it's statistically unimportant, what happens on threshold, because the width of threshold is infinitely small, and as a result, we can just ignore all the effects that happen on threshold. This is the point. Okay, we have pass packet density equals to N0 over 2. But yeah, but it was interesting question, and sometimes it also keeps this in mind that something can happen in between. Yeah, in some books actually you can meet the following proposal. So if you meet something right on the edge, then you need to toss a coin, and you need to have a coin or like special random generator that will generate random number. And then if it's larger specific threshold, you make decision for one region. If it's below some value, you make decision for another region. And if the generator gives you again value exactly on threshold, then you need to run it again until you get some concrete values at below threshold or above threshold. Yeah, you can use this random generator because when you have a decision right on the middle, theoretically speaking, that actually you just need to randomly make decision for one of two options, regions, and just go on. Okay, so we know that our pass packet density given by Moscow, so it's by Gaussian noise, and we show how pass packet density looks like. So it will be N0 over 2, it will be constant. And then if we calculate Fourier transform, we get the autocorrelation function corresponding to this noise autocorrelation function. And we remember that for white noise, autocorrelation function given by delta pulse. Delta pulse is the magnitude N0 over 2. Autocorrelation function of noise. Time domain, the white noise uncorrelated. Take the our autocorrelation function delta. And not over another way 2 times delta pulse origin. And then we need to calculate what will be the expected value of noise that we have in one branch and noise that we have in another branch. And we can calculate the expected value if we just substitute definition of noise in the branch. Yeah, what I mean, we already have definition of signal in each branch, which simply integral times basis function is input signal. And for noise, we have the same. We just take noise, multiply this basis function, and integrate over single interval. I mean, all the same. And here, if we just use this definition, we just take integral from 0 to capital T of some input noise at time instant t1 times J's basis function. It is integral over time interval or time that we denote t1 times 0. And of course, further we can say that we just have the same time scale for both processes, and then we can just, instead of t1 and t2, we have just t. But in general, we have to consider different variables for and have one time interval for one process and absolutely different time interval for another process. And t2 times another basis function, dt2. Now we have this, and first part corresponds to n j, and second part for n m. So then we can actually say, we can combine these integrals, and we can write that this can be written as double integral from 0 to capital T, both of them, expected value of n t1 times n t2 times, and then we get product of two basis functions, psi j t times psi j k of t, and times dt1 dt2. And something similar actually you will meet next semester in our communication course when we analyze when we talk about channel properties and when we introduce uncorrelated scattering assumption. Because it says that actually if you consider different, and because we have white noise, when we consider two different time instances, this expected value will be nothing else as a naught over 2 times delta pulse of difference between two time instances. So if you have two different time instances, result will be 0. But if you have the same time instant for both parts, then it will be a naught over 2, based on definition of white noise. So, and as a result, we can say that if we consider the same time instant, or we can say that, what should we say? A naught over 2 if T1 equals to T2, and 0 if T1 not equal to T2. And then, of course, it doesn't make sense to consider two different time instances because it will give us just result equals to 0. We can say that, okay, we consider the same time, let's say T2, and instead of this double integral, we get just one integral. We can say it will be a naught over 2 times psi j T2 times psi k T2 times d, or we can even write just t, just t, psi jt, psi kt, dt. This is our result. And again, now we need to analyze what happens when we have different basis functions, because before we were talking about different time instances for noise, but now we come to discussion about basis functions. And if j and k different indices that belong to different basis functions, the result will be equal to 0 because basis functions must be orthogonal. But if j equals to k, then we get that results will be equal to 1 because basis functions are orthonormal functions and energy equals to 1. And we can write that this result will be equal to a naught over 2 for j equals to k, when actually you just consider the same basis function, and it equals to 0 else. Or I can write for J not equal to K. And now we get interesting result. What it gives? It gives you power of noise. It gives you power of noise which corresponds to variance of noise. So if you know what's the input fast packet density, and you perform this, you use correlated weight receiver, you can find what will be the variance of noise after processing. Yeah, and actually it will be, it's not wide anymore. It will be band limited, and you have limited power, which equals to N over 2. So, and later on we will use this interesting result all the time, that we can get the power of noise if we know fast packet density of it. We know the variance of noise. And also we say that N1 and N2 in our case are statistically independent, because they are uncorrelated. This is the result of the last part. Okay, are there any questions about the materials we discussed today? Okay, if not, then that's all for today. We continue our discussion about discrete modulation schemes next week on Wednesday. If we have any changes in the way how we do tutorials, I will inform you. For now, we assume that we also do online, but yeah, I will send email in case of any changes. And I wish you a productive rest of the week. Thank you and goodbye.